All right, everybody. So what we're going to be looking at today are the ratio and the root tests, which are just going to be, two more tests that you can use to test series for convergence, just like you've been doing for a while now. But before we do that, I just want to mention a few limits that we can take and, that will hopefully make your life easier when we actually get to the ratio and the root tests. So without further ado, here's what we're going to do. So I guess the first thing is, let's look at this. Let's say I have a limit as, let's say, n goes to infinity of, I want the nth root of, let's just say, n cubed. Okay? Now, if you were going to evaluate that limit, the nth root of n cubed, you might want to write it like this. You might want to say, well, an nth root is actually a 1 over n power. And if you do that, that's actually a limit as n goes to infinity of n to the 3 over n. But it doesn't matter whether you do the third power or the nth root first. So you might as well do n to the 1 over n. Oops, that's not what I wanted. N to the 1 over n to the 3. And then using a property of limits, you could do what I was trying to do there. You could even take out the cube outside of the entire limit. There's a property of limits that say if the function is continuous, then you could actually do the function after you do the limit, or rather you could bring the limit inside of the function, either way that you want to look at it. So we have this. Now let's look at this right here. Limit as n goes to infinity of n to the 1 over n. Now, I'm not going to formally evaluate that limit for you, but what I am going to do is I'm just going to show you a graph, and then we'll know what this actually looks like. So let me find the graph. There it is. All right. So let's see if I can figure out how to get rid of my file manager. Okay, there we go. So I've got picture. I'm going to move it to where I want it. Make it a little bigger. Okay, there we go. So that's this function. This is y equals x to the 1 over x is what that is. Okay, and notice the scale. I had to go out to 800 here, but what you should be able to see from this is that as you head out to the right, the function is approaching 1, right? 1 is right here. So as you head out to the right, of course, it just approaches 1. So this limit here is actually 1 and then cubed. So 1 cubed, which is, of course, 1. So what I wanted you to notice about this is, first of all, the limit is 1, but second of all, the 3 doesn't matter at all, right? Like that 3, which I just carried through the entire problem, just ended up there, which just ended up there. But 1 to any power is still going to be 1. And so even though I did the limit with a 3, you would actually be able to conclude this. The limit as n goes to infinity of the nth root of n to the p is just 1. Okay, so I just wanted to do that limit, and we're just going to remember what the result was, and we can use it later. All right, the next thing I want to do is just mention a few things about the sizes of functions. So if you have a limit like this, let's see, a limit as, we'll say n goes to infinity, and I have let's say n squared over n cubed plus 1, right? What you're supposed to think about this is that the in the denominator, the function is larger. And so even though the top is going to infinity and the bottom is going to infinity, you don't want to think of it that way. What you want to think of it as is the bottom goes to infinity faster. So this is a bigger infinity on the bottom and a smaller infinity on the top. And so the result is going to be that this limit is going to be 0 because the denominator gets big faster than the numerator. And of course, you can do that with algebra. I'll do a little bit of algebra here just to show you. You should have learned how to do this in your Calculus 1 class. But what you could do is if you just, let's see here. How do I want to do this? In this particular case, what you would do is you would say, well, if I multiply the top by 1 over n squared and the bottom by 1 over n squared, then I would be able to turn this limit into the limit as n goes to infinity of n squared over n cubed over n squared plus 1 over n squared, which is the limit as n goes to infinity of 1 over n plus 1 over n squared. And then when n goes to infinity, what you're going to get is 1 over this n is infinity. 1 over n squared is going to be 1 over infinity, which is 0. So you end up with 1 over infinity, which is 0. All right, so that's a longer way to do the problem, but the way you ought to think of it is the way I did it over here on the left, because you don't have time in these problems to be doing this kind of thing all the time. Okay, so you want to just think of it big. If the big function is on top, it's going to go to infinity. If the big function is on bottom, it's going to go to 0. And if they're tied, then something else will happen. So here's the idea. Big infinity, small infinity is going to give you infinity. Small infinity over big infinity is going to give you 0. All right. If they're exactly the same, same infinity over same infinity, that's where you're typically going to have that case where you like divide, I'll say, ratio of leading coefficients kind of thing happening, which I'll show you an example of momentarily. All right, so that last case happens for stuff like this. So like the limit as n goes to infinity of, if I go like 5n to the 4th plus 3 over 7n to the 4th plus n cubed, right? Since they're both fourth powers and fourth powers are basically the same size, then the limit here would actually be 5 over 7. And you could get that using the method that I used here. But I'm not going to, right? So that's the case where it's the same type of function on top and on bottom. Now, in order to make this idea useful here, what you're going to want to know is, of course, what's big and what's small, okay? And so if you make a little picture here, not picture, but if you make a little kind of chart, so a logarithm is pretty much the smallest thing you're going to see. And then a logarithm is smaller than some kind of root. So like here, so like a, I don't know, fourth root or something. A fourth root is still bigger than a logarithm as n goes to infinity, but not bigger than most other things. Now, a fourth root would get beaten by like a square root, for example. right? If the power is bigger, then the function's going to be bigger. And an nth root would get beaten by an n to the first power, which would be beaten by a higher power of n. I'm putting an n cubed, but that's like representative, right? The bigger the number, the bigger the function. All of the polynomials are smaller than all of the exponentials. So like 2 to the n is bigger than any polynomial. Of course, that exponential is smaller than a bigger exponential. For example, all of the exponentials are smaller than a factorial, and a factorial is smaller than n to the n. All right, so that's kind of the relative sizes of functions. So you have over on the left, you have, small infinity as n goes to infinity. And over here you have big infinity as n goes to infinity. All right, and those concepts will really help you evaluate limits a lot faster, and it's very useful. So like if I'm doing examples, right, if I go limit as n goes to infinity, and I go like log n over n factorial, all you have to do is you just go in your head, you don't even write it, you just go, well, that's small, right? It's on the left. This is big. It's on the right. Well, that's going to be 0, right? Because the big denominator is going to win and make the whole thing go to 0, right? Just what I wrote here. Big infinity, small infinity. So we have a small on top and a big one on bottom. So it's 0. So you don't even think about that. Like when I see this, I'm not even thinking very hard at all, okay? So let's do another one, right? Let's try if you've got like n factorial over, 300 to the n, right? The denominator looks really big, but the denominator is an exponential and the top is a factorial, and exponentials are here and factorials are here. The factorial is bigger. It doesn't matter what the number is on the exponential. So again, you're just going to say, hey, well, that one's big, that one's small. It's small compared to the factorial. It's big compared to a lot of other things. So the big infinity's on top, so that's going to be infinity. All right, and when you combine these, you can still use the same ideas here. And so like limit as n goes to infinity, if I go, what do I want to do? Yeah, so like if I go n log n over n squared plus 2, for example, that's a little bit more complicated than we had before. But what you want to do is you want to think about this as this is n times n, right? And this is n times, well, I'm just rewriting it, n times log n. Well, that means that we know that log n is smaller than n, right? From up here, log n's right here, n's way over here. So log n is smaller. So if you have n log n over n squared, then that means that the n log n is the small one. So this has a small numerator and a big denominator. So that limit's 0. Okay? And this kind of thing is how people, like, it's the difference between how people who are good at this do this and how people who are, like, haven't done enough of it yet are doing it, right? You need to save time and effort in these problems whenever you can. So you want to understand this so you can do that, right? And you can verify any of these like easily using like Wolfram Alpha. So like if I go Wolfram Alpha, and I go limit of, and I can pick any kind of limit I want here. So like if I go n squared over e to the n, as n goes to infinity. Now what should happen? N squared over e to the n. So I have an exponential on bottom. That's going to be the big infinity. So this should be 0, right? Yeah, so it's just 0. And but you don't need Wolfram alpha, because now you know about which functions are bigger than which functions, right? If I take this one, what if I go log n times, what do I want to do? How about ln n? So I'm putting 2 logs on the bottom. By the way, I think Wolfram alpha interprets ln n and log n the same. So even though I typed them in differently, I think it's the same. So what's going to happen here? N squared on top, log n on the bottom. Well, the logs are smaller, right? So n squared's bigger, so this should be infinity. Yeah, see? Infinity. All right? So using these kind of things will really help you, again, save some time here. Don't know what kind of pictures somebody had up in Discord. That was a 3D modeling Discord there. Dismiss. Oh, you can't see what I'm looking at right now. I was looking at the Notability screen when I said dismiss. All right. Wait, that's not our notes. Whoa, hold on. Oh, okay. You couldn't see what I just saw, but I added this assignment or this lecture notes in the wrong section, and I could have, like, they weren't there anymore, and I was like, oh man, we're 17 minutes into the video and I have to start it over. That was going to make me so sad. All right, so enough of that. So we looked at big infinities versus small infinities, and that will really help us a lot. Okay, actually there's one more. Let's do one more that we're missing here. What about this one? One last good thing to know. What is the limit as n goes to infinity of the nth root of n factorial? It's a good one, right? Well, guess what? I'm not going to prove it. I'm not going to do this. I'm just going to go to Wolfram alpha. We're going to do it on Wolfram alpha. Nth root, n factorial, what's the limit? We're going to write it down, and then we're going to know it. Limit of, what did we say? N factorial. And then for the nth root, I'm going to have to type it as 1 over n as n goes to infinity. Probably 1, but let's look. Oh, it's infinity. Oh, it's infinity. All right, well, good to know, right? Nth root of n factorial is infinity. Cool. So let us, oh, I have to do that again. Close this. Again, don't know what they're up to on Discord there. Looks inappropriate. Actually, I think what they were doing was they were doing 3D modeling of clothing. And so they had like 3 figures wearing like dresses that they modeled or something in a 3D modeling program. Anyway, let us do this. So okay, what are we doing? Oh, it's gone. It's gone. It's gone. Of course it's gone. So what was the one we decided to do? One last limit. Here it is. We did the limit as n goes to infinity of the nth root of n factorial, and that one was in fact infinity. All right, cool. That is useful to know, and we should be good. So now we can actually start what we're trying to start today, which is the ratio test and the root test. So I think I'm going to write them both down so they're here for you. So here they are. So ratio test. Ratio test. So the ratio test says this. So suppose the limit as n goes to infinity of absolute value a n plus 1 over a n equals L. All right. Then there's going to be three cases here. If L is less than 1, then the series 1 to infinity of an is absolutely convergent. Now you can just read that as convergent if you want. You don't need to worry about the absolute part. It's absolute though because of the absolute values that we put in the formula up there. If L is less than 1, nope. If L is greater than 1, the series just diverges. And if L equals 1, then the test didn't work. Test is inconclusive, and you have to do another test. All right? That's the ratio test. Now the root test, which we're also going to write here so it's down on paper. Root test. So suppose the limit as n goes to infinity of the nth root of an equals L. So it's got a root. Then how do we interpret that answer? Actually, same exact way. So I copy pasted it. All right. And there you go. That's your root test and your ratio test. Now, of course, what we need to see is how do you actually apply these things? Okay. And before we do, I'm going to have a warning for you. Warning. The ratio test, ratio and root test don't work on series that are like P series. Right? So remember what P series are, right? They're like 1 over n to the P. And the ratio and root tests don't work. When I say they don't work, what I mean is that they're going to come up inconclusive every single time. Inconclusive, L equals 1 every time. So you shouldn't use the ratio and root test on a test that looks like a P series. So like examples, if you have something like this, let's say 3 to the n over n factorial, that's a good ratio, root, good idea. Okay? Whereas if you have one like this, 3 over n squared plus 4, ratio, root, bad idea. Okay? because that's basically like 1 over n squared, which is a p-series. So you would not do ratio or root test on it. It will not work. Okay, so that's just a warning before you start. Okay, so let us do some of these now. That is not what I wanted. Okay, here we go. Problems. Okay, excellent, excellent. So here is a problem straight from the homework. Here's a series. N goes from 2 to infinity, 15n to the n over ln n to the n. It's hard to read. ln n to the n. And then it says, basically, what are the results of the root test? What does root test tell you? Question mark. And your choices are converges, absolutely, diverges, or no information, right? So the 3 choices for L. So what you do is this. So you start with your formula, right? Start with the limit as n goes to infinity of the, what is it? Nth root, absolute value, an. So that is the limit as n goes to infinity of the nth root of 15n to the n over ln n to the n. I don't need absolute values because my terms are already positive, so just drop the absolute values. Okay, now when you're trying to work this out, you generally want to use the root test when you have powers of n like we do here, because you can split up your root like this, and then anything that has an nth power, right, an nth root is going to cancel with an nth power. An nth root is going to cancel with an nth power. And so what you're going to get is going to be simply the limit as n goes to infinity of 15. Wait, I left off an n, didn't I? There's a missing n here on the 15. Okay, so you're going to end up with 15n, and then on the bottom, you're going to end up with ln n. Okay, and then we need that limit. And that is why we needed to learn about these limits. Okay, so what do we have? N on top, ln n on the bottom. So remember, based on what we have here, n is bigger than a log. N is bigger than a log. So that means on this limit, the top is going to be big and the bottom is small. And so if you have, well, and they're infinity, right? Because we're going to infinity. So which one, or what's the result there? If the big infinity is on top, then you get infinity. So this limit is infinity. Well, what's that say? We need to interpret it according to our formula. So our choices are L less than 1, L greater than 1, L equals 1. Obviously, L is greater than 1 because it's infinity, right? We have infinity, then we're greater than 1. So that's it. Come down here and you say, since L equals infinity is greater than 1, series diverges. And that's the root test. Okay, so you do the root test when you have powers of n, because it just cancels out the powers of n. So when I saw this at the beginning, those n's, I go, oh, that's good. We'll take an nth root and they'll disappear. All right, next one. Okay, excellent, excellent. Let's try this. Oops. Same thing. What does root test say? About this 1 over 6n to the 6th. All right. Now, this is n to the 6th. That's not an exponential. That is a power of n. That means we're looking at a p series. We're looking at n to the 6th, which is a p series. So what's going to happen? I already told you it's going to be inconclusive, but let's apply it just so we can see. What does the root test say about this? Inconclusive, but let's do it. So if we're going to work this out, we need the limit as n goes to infinity, nth root, an, absolute value, which I didn't do this on the last one, but I want to here just to make sure we're on the same page here. An nth root is actually in a 1 over n exponent, right? And then we have 1 over 6n there to the 6th. Actually, you know what? I want a root. I don't know why, I just do. Okay. So there you go. So, limit as n goes to infinity. Again, you split up the root. Nth root of 1 on top. Nth root of 6n to the 6 down there. Okay. So let's see here. Oh, they said to do the ratio test is what I'm seeing, but oops. All right, so anyway, it's fine. 1 over, and then we have the nth root. Actually, I'm going to break this up here. Hold on. The nth root of 6 to the 6 and the nth root of n to the 6th. Okay, now I realize that there's one of these that we didn't do because we have this and then we have this. Now the green one, right, the nth root of n to the 6th, I think we wrote that down somewhere. Right? Where is it? Oh yeah, no, that's a factorial. Where did we do it? Ah, right here, right? Nth root of n to the p is going to give you 1, whatever the p is. So our p is 6. Okay. Now, the other thing I want to do, though, is I do want to actually, I'll work this out properly. So 1 over, this is 6 to the 6 is just a number, and then that's to the 1 over n, right? And then this is, I'm going to leave it the way it is. Okay, now, we're going to take the limit now. So when you take the limit of the left-hand one, 6 to the 6 to the 1 over n, that's 6 to the 6, 1 over infinity, because we're taking the limit now, is going to be 1 over infinity. That's a 0 exponent. The other one here, the nth root of n to the 6, we know the result is going to be 1. And then this is 1 over 6 to the 6 to the 0 times 1. And anything to the 0 power is 1. So 1 over 1 times 1, which is 1. Okay, so we get 1. Now what does that say? I'll write my conclusion here. L equals 1, so test inconclusive. All right, now they told me to do that with the ratio test, and I just did the root test because I don't know, because I wanted to. On a lot of problems, both tests will work, but the reason they told you to do the ratio test is because they didn't want you to have to work out that limit. But we worked out that limit ahead of time, so we actually know that that limit's 1. So it's okay for us, but they didn't want us to have to do it. Okay. Well, we did 2 root tests. Let's do one that is ratio. That's another one exactly the same. Give me a ratio one I can do. Come on, guys. All I want. These are so dumb. So by the way, what we just did, this inconclusive one, the computer just decided I needed to do like 5 of those in a row. So, you know, keep that in mind. This is really weird. Okay, they really don't have any that are root tests that are not inconclusive, it looks like. That's very, very strange. Okay. I'll just make one up. So, sorry. Example. Use ratio test for, and I'll just make one up. It's not that hard to make these up. So what do we want? I want 3n squared over, I'm gonna go in factorial. Okay, now before we do this though, and we'll start this at 1 here to infinity, not that it matters. So in order to do this, you need to know about factorials, which I think we did this once before, but I'm going to remind you. So remember that like a factorial is something like this, like 1 times 2 times 3 times 4, right? That's a 4 factorial. And like a 5 factorial would be 1 times 2 times 3 times 4. And the reason, times 5. And the reason I'm writing these down is because I wanted to remind you that if you have a factorial, like 5 factorial, for example, you can write 5 factorial as like 5 times 4 factorial, right? Because the 4 is numbers 1 through 4, and then if you add the 5, then you get a 5 factorial, okay? So you can split off the top number, basically, right? We split off a 5 and we were left with 4 factorial. And you can do that even when it's n. So like, if you have like an n plus 1 parentheses factorial, that's just n plus 1 n factorial, if you want. If you have a bigger one, you're going to see stuff like this sometimes, like 3n plus 2 factorial. Sometimes you'll see something like that. And what you could do is you could say, oh, well, that's 3n plus 2. And then I would have 3n plus 1 factorial, right? This number is 1 less, just like the 4 is 1 less than the 5. And then you could do it again. You could say, well, 3n plus 2, I could write the 3n plus 1 factorial as 3n plus 1 times 3n factorial. Okay? And breaking up factorials in this way is how you go about simplifying them. Okay? And we're going to need to do that here, although it won't be that complicated. All right. So let's go ahead and do this. So we're going to apply the ratio test this time. So let us do that. So we're going to evaluate the limit as n goes to infinity, absolute value. Ow, my shoulder hurts. an plus 1 over an. Okay, so you start there. So what you're going to do is figure out what these are. So an plus 1 is the top, or it's the formula, but with the n's replaced with n plus 1. So you replace the n with n plus 1. So what you're going to get for an plus 1 is 3 n plus 1 squared over parentheses n plus 1 factorial, right? You see why we're talking about these? That's a n plus 1. In the denominator, we have an. An is just this exactly as it's written, so just 3n squared in factorial, right? Now your second step is when you're dividing by a fraction, that's multiplying by a reciprocal. So divide by fraction means multiply by reciprocal. So limit as n goes to infinity, absolute value, the top fraction, just write out the top fraction, and then times the bottom fraction, but upside down. So you're going to take this and you're going to flip it upside down and have n factorial 3n squared. Okay, so this is what you get. Now, what you're supposed to notice at this point is that certain terms look alike. Like this one looks like this one, and this one looks like this one, right? You have two factorials and two non-factorials. So I'm just going to rearrange this. And we just want to put stuff that looks alike right above what it looks like. So like n factorial on top, n plus 1 factorial. Put the two factorials together. And then the ones that aren't factorials are 3 n plus 1 squared and 3 n squared. Okay? Now, let me just rewrite that actually. Well, no, I'm not. Copy paste it. So look at this. Now, what you're going to do for your factorials is we're going to simplify them. Now, yeah. So let us get to the point where we can. So you've got n factorial on top, and then on bottom you have n plus 1 factorial. But n plus 1 factorial is n plus 1 n factorial. So n plus 1 n factorial. That's so we're going to be able to cancel the factorials. Now, the other fraction, 3n squared on bottom, there's nothing to do there. On the top, though, you've got this 3n plus, or 3 parentheses n plus 1 squared. Now, I'm going to multiply that out, but then I'm going to say something about it. So you have 3 parentheses n squared plus 2n plus 1. Okay? And now I'm just going to recopy it. Almost recopy it. Actually, I'm going to move this over. Not quite what I meant. So what was I doing? Oh yeah, so you can cancel this anytime. So let's just cancel those factorials right now. And then we got 1 over n plus 1 here. And over here, you multiply this out, and you get 3n squared plus 6n plus 3 over 3n squared. Okay? Now, what I wanted to mention, though, is this. Now, I just multiplied that all out, but I did not need to, because when I'm taking this limit right here, which I'm going to do right now, let's take the limit. When I take the limit right here, well, first of all, this is going to be 1 over infinity, which is going to be 0, but let's just say we don't know that yet. And then the other one, right here, you're going to be looking at the 3n squared and the 3n squared, right? They're both n squared, which means we're in the case where you're going to take the ratio of the leading coefficients, which is 3 over 3, which is 1. So then this is 0 times 1, which is 0. Okay, so that's my limit. But what I wanted to make a point of was way back here. Without multiplying out the top, you should be able to look at this and say, okay, well, you're going to have an n times an n to give you this n squared, right? So n times n is n squared, and then n squared times 3 is going to give you 3n squared. So you should be able to look at this and predict the 3n squared. And then you should not have to actually multiply this all out, because I don't even care about the 6n plus 3. So why did I spend time calculating it, right? So that's what we should have done. There were other ways to do it too. Like I could have done it this way. Another way to evaluate that, I could have done this. Or when I had the limit as n goes to infinity of 3n plus 1 squared over 3n squared, I could have written that as, well, first of all, I realized at this moment that I should have canceled the 3's. That would have been smart. And then what I could have done is I could have written the fraction as n plus 1 over n quantity squared. And then you can just do this limit in here, which is going to be, again, because it's the same power, 1 over 1 and then squared, which is 1. So there were a lot of ways to work out this limit right here. But we did anyway, and we got 0 for the final result. All right, so what's that matter then, right? Point is, L equals 0. What's that mean? L equals 0, that's less than 1. So the series converges absolutely. All right. So that's the ratio test. Notice the ratio test, even for a relatively simple example, does take a lot more writing. So generally speaking, the ratio test is easier, but there's more writing involved. And the root test is more complicated, but there's less writing needed. That's just my opinion. All right, let's do maybe one or two more. I lost the homework. Where's the convergence test here? All right. Oops, that's not what I wanted. Root test, sorry. Okay, there we go. All right. So what was this? What one did we just do? Okay, one more of these. Example, use ratio test for 6n to the n over n factorial. So notice that what they like to do is if you've got factorials, they like you to do the ratio test. And the reason they do that is because we did this limit up here somewhere. Hold on. We did it right here. We did this limit, but if you didn't do that limit, then you wouldn't know what that limit was. And so that's why they mostly ask you to do the ratio test. Makes it easier to deal with the factorials. But we are going to do the ratio test because they say to, not the root test. So let's try this. So what are we doing? We're doing the limit as n goes to infinity, absolute value, an plus 1 over an. If you want, notice that we had to, like, we wrote it out this way, and then you had to rewrite it with the bottom flipped upside down. If you want to skip that so you can do one less line of work, then you might just want to remember it this way. Instead of an plus 1 over an, maybe you can remember it an plus 1 times 1 over an. Think of it that way, right? Because this is just an upside down an. That'll make it easier. So let's do it. Limit as n goes to infinity, absolute value. Yeah, okay. So what are we looking at? All right, an plus 1. So remember what you have to do. You have to replace all of the n's with n plus 1. So we're going to have 6 n plus 1 to the n plus 1 over n plus 1 factorial. That's hard to write and get the parentheses all in the right place, by the way, isn't it? I think it is. And then times 1 over an, which is an an that's upside down. So that's this, but upside down. So the n factorial is on the top, and then the 6n to the n is on the bottom. So there we go. Now, there's some stuff we need to do. I do need to group terms and all that kind of stuff, but not yet. What I want to do is, let's just multiply this out first. So 6n plus 1 is 6n plus 6 to the n plus 1. So I can clear out some parentheses there. That's nice. All right. So we're here. Then you want to kind of, rewrite to group your stuff. Group like terms basically is what you're trying to do here. Limit the n as n goes to infinity, parentheses, square brackets. So put like the 6n plus 6 to the n plus 1 over 6n to the n. Those are alike. And then your factorials, n factorial, n plus 1 factorial. So I got your factorials. Then we need to figure out how we're going to simplify this. So here's how I'm going to do it. This is an n plus 1 and this is an n. That makes it hard to simplify. Not really, but I want those to match. So what I'm going to do is I'm going to write the 6n plus 6 as 6n plus 6 to the n, and then 6n plus 6 to the 1. That way I have it to the n power somewhere. All right. Let me just move that up. That. Then for the factorials, I know that my n plus 1 factorial is n plus 1 times n factorial. So I'm here. Right away, I can cancel my factorials. So let's do that. Now this n plus 1, you could either leave it there, or you can start to figure out how to cancel it with the 6n plus 6. But I'm not going to cancel it with the 6n plus 6 because I don't think I need to yet. So I'm not going to worry about that at the moment. What I am going to do is I'm going to worry about this to the n, this to the n. So what are we going to get? We're going to get limit into infinity. I'm going to get, let's put those together, 6n plus 6 over 6n, all of that to the n. Then I've got I guess I'm putting the 6n plus 6 by itself now. And then I've got a 1 over n plus 1, like that. So I kind of separated these yellow ones into their own fraction. Okay, so far so good. One more, I'm rewriting it. I am not touching that first fraction, so I'm just going to leave it alone. 6n plus 6 over 6n to the n. What I am going to do on the second fraction is I am going to factor out that 6 because I do need to, it looks like this. Writing it this way, I can see that I can cancel the n plus 1s, like so. And now let's try to take our limit. So think about how to do this. So right here, 6n plus 6 over 6n. When n goes to infinity, that's going to be 6 over 6, which is going to be 1, to the infinity, which is going to be 1 to the infinity, which is 1. And then the middle one, there's no n's, it's just a 6. And then the last one, there is no last one anymore, right? So the last one is just 1 here. So what am I going to get? 1 to the infinity. 1 to the infinity is 1, so I get 1 times 6, which is 6. So the limit is 6. Okay? So then what are we going to do? We are going to kind of make our conclusion. So we're just going to say L is 6, which is bigger than 1. If 6 is bigger than 1, then the series diverges. Okay? So you got to see how to simplify a few different types of things here. Okay, so yeah, I think that's everything that's in this section. It's not the easiest section, but you'll get by. Good luck. See you in the next lecture, I guess.